Now I'd like to call up on stage Professor Anirban to talk about nearest neighbors.
Okay. Wow. Welcome everybody. This is a pretty successful first meet, I'd say. I was asked to talk about anything. So I picked something that's close to my heart. So I don't know how much Python knowledge I'll be imparting to you, but I don't know much of Python anyway. So let's see. So how many of you have heard about nearest neighbors? Okay, nice. So at this point, I think I could pull the Khoja Nasiruddin trick, right? I could potentially ask this half of it to sort of explain to the other half what nearest neighbors is, and I could potentially vanish. And anyway, we can possibly discuss some interesting point. Maybe there will be something interesting. So a lot of these slides are courtesy this one person, Erik Bernhardsson. He's a character who will make appearance later in the talk. I think currently CTO of Spotify, which is a music streaming company, and we'll see how he comes into the picture. So nearest neighbors. So without much ado, what is nearest neighbors? Okay. So here's a simple definition. You start with a bunch of points. I don't care what the points are, right? They are points in some space. Okay. And now what you're asking is that you're giving this query point, right? Which is also a point in this space. And you are okay at this here I've drawn a circle. It's not necessarily it doesn't necessarily need to be a circle. You are just asking a question of give me the nearest neighbor of this blue point from among the points that you have. It's that simple. Okay? You could ask about the nearest neighbor. You could ask about the 10 nearest neighbor. You could ask about 100 nearest neighbors. You could ask about the nearest neighbor, all the nearest neighbors within a specified radius. And these are all different variants of the same question. So why is this important? Okay? This is about maybe we did it with a slightly larger radius, and so on and so forth. So why is this important? To see the ubiquitousness of this question, we got to get back to why am I talking about points? What are points? We're doing data analysis, right? And points are things that we have seen in geometry. I mean, not beyond that. But it turns out that representation of data as points is pretty universal across any field of data science that you see, right? I mean, whether it be images, which are pretty easy to imagine as points. You just linearize the image. If it's a 256 by 256 image, RGB, maybe you can represent it as a vector in 256 squared times 3 number of dimensions, okay? Documents, sparse vectors over words. Right? You could represent, I could represent a document in terms of, let's say, just as a set of the words that it has, and that I could represent as a Boolean vector over the number of dimensions, which is each dimension corresponds to a word in the English dictionary. Interestingly enough, we could represent the words as vectors over some corpus context. What does this mean? We'll see some examples of this maybe. So you could imagine that, imagine a particular word, let's say PyData, right? I could search if I have a large enough corpus, right, let's say of technical documents, I could search the corpus and see what is the context in which this particular word is appearing. This particular word, PyData, is appearing, right? So what do I mean by context? I mean, it's not very clear what I mean by context. I mean, it's sort of, it's more of an art. You could say that I could take the k-grams, the few words that appear right before PyData, few words that appear right after PyData, and that defines the context of the word PyData. So why is this important? So imagine that you are given the word apple. Now what does it mean, right? Of course, it depends on the context, right? I mean, am I referring to the operating system of my notebook? Am I referring to the New York City itself, or am I referring to the fruit, right? Potentially, if you take the context, right, and if I have a representation of the word in terms of the context, I could disambiguate these meanings, right? This is called word sense disambiguation. Okay, and there are very nice representations of these of words, and in case you have not heard about some of them, one of the most popular ones that we use is called word2vec. It's called word2vec. So what Google did was that it took all the documents that it had at its disposal, right? It created this context, and for like 10 million English words, we now have a very interesting representation of these words. So why interesting? Let's see an example. But before that, I mean, users can also be represented as vectors, and we typically do this. If you are in a web company, you have users, When did I start? Okay. We have users, and we need to do something with these users. We want to recommend them something. We want to make sure that they have an enjoyable experience. And for that, I need to sort of have some knowledge about the users, right? And the way we typically do this is that let me sort of create a representation of a user in which each dimension, it's again a vector, and each dimension maybe represents, okay, the number of times this user visited, let's say, the Google front page, number of times the user accesses Google Mail, number of emails that they sent, right? Number of Google properties that they visit, how much money did they spend in Google Pay. These all could be dimensions. And now we could have a pretty huge dimensional vector that captures basically everything that the user has done, right? In Google or Yahoo or whatever, right? So or even what the user has read, the kind of things that they have read. So what is the use of this? Right? As you probably have guessed, that once we represent these users as vectors, right, and once we can answer questions like finding out the nearest neighbors, I mean, it turns out that even this very simple primitive can be fitted into a huge number of machine learning applications. Right? Some of these are fairly obvious. For instance, there's a very famous classifier called the nearest neighbor classifier. What is a classifier? Very simple, right? If I am friends with 5 people and majority of them happen to be income tax evaders, I'm potentially income tax evader. That's a good guess, right? That's I mean, this very simple strategy can again be modified into. I mean, you can make this more complicated by sort of trying to define the notion of distance, right? What do I mean closest, right? How did you measure this distance? It doesn't really need to be something as simple as L2 or L1. It can be even more complicated than that. You can even learn the notion of distance according to which this is true. Okay. Another popular use that I have seen is in sort of finding out near duplicate web pages, right? Near the basic problem is very simple. So there is this crawler in any web search engine that goes out and crawls these web pages, right? And see, this crawler is pretty dumb by itself, right? Because you just provide it just is doing a BFS over the web, right? Now you don't want, because a single page can have multiple mirrors, right? I mean, if you have read these news articles from Times of India, you can potentially find the same news article in another web page because they're all supplied by PTI, for instance. They're all written by PTI. So the same article can appear multiple times. The same web page can be mirrored in multiple locations because variations in let's say the dynamic parameters of the URL, right, can cause multiple URLs to basically load the same page. And but you won't. I mean, you don't want to keep multiple copies of these pages in your index, right? In the search index, because then the search index would blow up a lot, right? So you want to deduplicate it. That's one reason. Another obvious reason is that if you're presenting the search page, right, you don't want to present multiple results that are the same, right? You want to make sure that each result is kind of distinct, right? So that's another application of this near duplication. So why am I calling it near duplication? Because these pages are not always exactly the same. Why are they not exactly the same? Well, because ultimately it's HTML, right? So maybe the HTML wrapper is different. Maybe there was an ad in one of the pages that's not in this page. Maybe the font is different, something. I mean, somebody added a little bit of HTML, and so the entire sort of, so it's not exactly a duplicate, right? So this is called a near dedupe problem, okay? And it turns out, I mean, these turn out to be surprisingly hard problems, even if you sort of try to formalize it. In search, right? I mean, so potentially, I mean, given a particular query image, you could try to search for similar images. Clustering, recommendation, right? If you have seen a bunch of movies, I could then ask, okay, what is the next movie that I want to recommend? And maybe it's kind of similar, but not exactly similar. See, I mean, if you are paying attention, you'll already notice that this level of that what I call near, right, is kind of getting more and more diffused over this range of applications, right? Because in nearest neighbor classifier, you potentially want a very tight definition of what I call near. Near duplication, very tight definition of what I call near. In recommendation, if you're using it if you're using near neighbor query in recommendation systems, you probably want a slightly looser definition, right? Because if I have seen, Harry Potter DVD version, I don't want to see the Harry Potter Blu-ray version, right? So because they're basically the same movie, okay? So I mean, but all of these can, I mean, do use some version of the, I mean, there are algorithms for each of them that do use some version of this nearest neighbor query. And of course, if you go to people from any of these companies, I mean, you'll probably find tens of users in each of these companies. Okay? So I mean, practically, it's a pretty important problem, right? So let's see a very concrete small application of it. So this talk is very non-technical. So I mean, it's not going to have any formula. I think this is probably the only formula, possibly so in the talk. So here's a very simple application, right? I guess most of you have heard of MNIST images. So I mean, but just to put all of us on the same page, these are really handwritten digits. So you have a bunch of examples of 2 being written, bunch of examples of 6 being written, 7 being written, and so on and so forth, right? And typically one of the machine learning tasks is that, can you learn a classifier to distinguish, to kind of, given an example of one of these, can you say that this is 6? This belongs to the class 6, okay? So, I mean, here's one particular way you would apply this. You would apply the nearest neighbor classifier, right? You would I mean, these are all 28 by 20 dimensional images, and I can represent them using a 794 dimensional vector. I could define the distance between any two vectors. Let's say simple L2 distance. These are all grayscale images, right? So the values range between, each coordinate ranges between 0 to 255. And I define the distance using a simple L2 distance. And then I could ask for a nearest neighbor, right? Basically, I say that, okay, given this query image 2, right, find out the 10 nearest neighbors. And if all the 10 nearest neighbors are 2, right, I say that this query image is also really represents a handwritten digit 2, okay? And so on and so forth. But maybe, I mean, sometimes things go wrong. If you say that this is 8, right, one of the closest images could turn out to be this 5, right, or 6. For 6, it turns out to be 0. A slightly better way of doing this is not to work with the original high dimensional vector, but to work with a slightly lower dimensional vector, because I know that the input is kind of low dimensional. So what I mean, any self-worthy data scientist would do is that project it into some low dimensional vector, although she would not know what low dimension. That would be that would come out by experience and by sort of trying it out, and then work with this low dimensional vector and do the same thing. I mean, once you get a 10-dimensional vector using, let's say, principal component analysis, or if you want to be more fancy, non-negative matrix factorization, whatever you want to do, right? And then get a 10-dimensional representation of every point, of every image, and then again ask the nearest neighbor query, right? And then apply some kind of majority or something smarter. Okay. So, as such, then let's try to formalize a little bit what this nearest neighbor query means, right? I mean, again. What you would be given is a bunch of points, a bunch of vectors points, right? And you can apply any kind of preprocessing you want on these points. Okay. We don't count that, let's say. Right? At query time, you will be given a single query. Suppose you're given a single query queue, right? And you have to answer, right? You might be asked. Let's say there are 2 variants of this question. One of them is that given a particular query queue, you're asked to return the k nearest neighbors, right? For instance, if I'm asked to return the 1 nearest neighbor, it would be this. The 2 nearest neighbors, maybe it is this and this, right? You have to return these 2 points, these 2 blue points, right? This is one variant of the question. Another variant of the question is that you might also be given a radius along with the query, and you're asked to return every point within this radius. So let's, I mean, any one of these variants, we solve most of the practical questions that we were dealing with. And it turns out you can reduce one to the other, although the reductions are, I mean, basically, yeah, you can reduce one to the other. That's not very complicated. What is a naive solution for this? Okay, so here's one naive solution, right? So suppose there are n points. So n is the number of points, and I forgot to write this, and d is the dimension in which each of these points lie. Okay, so naive scan would take nd time, right? Because you take the query point, you compare it with everybody, comparing it with 1 point takes time order d, comparing with n points takes time nd. So obviously I can do it in this time, right? Can I do it in much less, right? And what we are more interested in is that typically, everybody's okay. So typically n is much larger than d, Because as I said that most of the times what we do is that even if the data is high dimensional, I mostly project it into some low dimensional space and then work on it. So there was some slide missing on the what to vec, but anyway we'll see, maybe it will turn up somewhere. Right, so typically n will be much larger than t, and what we'll be more interested in is that can I do it in small o of n time. Okay, so what do I want to do? That I am allowing you pre-processing. I'm not counting the pre-processing time, right? But when the query comes, right, can you return me, let's say, the nearest neighbor, right, in small o of n time? This is the formal question. Okay, and can I do this? It's not clear that we can do this, right? I mean, it's not obvious, and in fact, it was not obvious for a very long time that we can actually do this for all data sets, right? At this point, what I want this to is to happen that your algorithm should work for all data sets, worst case analysis. Okay, so here is one possible way, right? That suppose you create what is known as the Voronoi partition of the point set. So when I said that I cannot do this, I sort of lied a bit, because here is an obvious way. That so if you don't know what Voronoi partition is, it's very simple basically. You sort of take these points, right, and then you try to mark out the region in space that sort of says that which are the points in this two-dimensional space that is closest to this point than to any other point in your data set, right? And it's going to have a picture like this. I mean, if you have 2 points, it's very simple. It's just a line, the Voronoi partition, right? If you have d point, if you have n points, it kind of looks like this honeycomb structure. Not exactly honeycomb, of course, but some partition like this, right? So what if I sort of given them, I mean, because I said that pre-processing is free, right? Then what if I sort of create this Voronoi partition, right, and just store this Voronoi partition with me. Right? Then given a particular query point, I'll just check which Voronoi partition it falls in, right? And if it falls in this one, then this is the closest, then this is the nearest point, and I'm done. What is the problem with this, right? So this will give exact answer, of course. The problem is that the structure of this Voronoi partition is pretty complicated in high dimension. In particular, if you have n points in d dimension, right, number of surfaces in here, number of separating surfaces between the planes could be of the order of n to the power d by 2. Okay, and given a particular query point, right, just trying to figure out which Voronoi cell it falls in takes a lot of time, given that is not very clear. Okay, that's the part I wanted to be little of, and query time.
So there might be many answers for Voronoi partition, because the point has many.
So what I'll do, see, the Voronoi partition really marks out the region in space such that any point in this region, for any point in this region, the one DNS neighbor is this. So then my sort of naive solution was that given the query point, see which Voronoi partition it falls in, and the owner of the Voronoi partition is your one nearest neighbor. Right? So of course, if you're looking for 2 nearest neighbor, 3 nearest neighbor, it might become more complicated. But the point is that even this is pretty expensive, right? Because given a query point, how will you do it in small o of n, right? Check the, which cell it belongs to. Might be possible if the points actually lie in some low dimensional. Maybe the points are in high dimensional, but they have a low dimensional representation. Okay? Maybe not, right? Because I don't want to rely on that. So it turns out that you cannot do this exactly in small o of n. How will you use this? If you want to know k nearest neighbors, I don't know, this is not that obvious how to use it, right? Because you take out one, then what do you do the second one? Maybe you create the Voronoi partition of 2 nearest neighbors or something. I don't even know how that would go. No, it's not clear to me actually. It's not clear to me. Yeah. So it turns out that you can say, right, that you cannot do this for all. I mean, in the worst case sense, right, in small o of n, if you are looking for an exact answer, and if you are looking for a deterministic algorithm, right, either of them hold true, you cannot do this. So you have to give up on 2 things, right? You have to give up on the fact that that you're looking for an exact answer. You have to give up on the fact that you want to be always correct. Okay, correct meanings that you have to accept the fact that your algorithm can sometimes fail. and then suddenly a lot of doors open for you, right? But that is the sort of the theoretical part. It turns out that this particular problem, a lot of people from both the applied side as well as the theory side have looked at this and will sort of see us a number of the possible solutions, sort of sketch through the space of it, right? One possible sort of, I mean, a huge, see in sort of CS, my view is that there's really two data structures, right? One is tree and one is a hash table. Everything else that I see is a function of these two. Sorry, this is too much of a simplification, but anyway. So, and then there are really two types of solutions here. One is using a set of trees and the other is using hash tables. Okay, so how do I use trees? So I create a space partitioning of tree, of the space, of this space, right? In the sense that what I do is that let's just divide the set of points arbitrarily at this point. I'll tell you how to divide later. We'll see some examples into two parts, right? And I create the root node to be the partition, left. Points on the left of the partition go to the left, point left of the tree, point on the right of the partition go to the right of the tree. Okay? And now I keep on doing this. Right? So basically I have the entire tree and maybe the points are the leaves. Okay? So now given a particular query, I can again follow down this partition and I can try pruning out parts of the tree, right? And try to follow this and go down to the leaf. Maybe near to the leaf or maybe somewhere down the leaf, I'll find the set of nearest neighbors. So I'll find the nearest neighbor of this particular query. Okay. So it all depends how we partition. I mean, what I just described is a very, very 100,000 feet level sort of view of this. And a lot of this is maybe incorrect depending on your implementation. It all depends on how you partition and how you are searching and so on and so forth. There's a lot of variance, of course, of this. Right? So before we do this, I mean, here is an example, right? I mean, let's say that this was the data set points that we started out with. I created the partition. So it would create a root with, it would create a tree where one side would contain this and the other side would contain this, right? And then you sort of do this partition again, right? So this might contain this part and the tree here might contain this part. The tree there might be contained here. And I mean, under this tree, this subtree, and the tree here might be contained under this subtree, right? And then you keep on doing this, okay? And then finally, when you potentially stop when you have a small number of points, okay? You could do this. How did I draw these? How did I draw these lines? Okay, so before telling you how to draw the lines, I mean, given a particular query, what do you do? So there's a lot of variations, as I say. You could kind of go down the tree in what is known as a defeatist search. You could sort of say that, okay, the query falls on the left side of the first partition, so I go to the left only. It falls on the right side of the second partition, you go to the right, and then you sort of follow the tree very faithfully, follow the partitioning very faithfully until you get down to wherever you want to go. Let's say you might stop when you have some, according to whatever heuristic. You say that, okay, I stop when the size of the subtree is less than 100, and then I search everybody. So this is called as defeatist search, right? You could do something more clever. You could kind of do a descending search, which sort of says that, okay, when I go down, I try to maintain my. So this is more like backtracking, right? That you would backtrack. That you kind of maintain what is my current nearest neighbor, what is my distance to it, right? And then I try to reduce that at every step. Right? You could kind of maintain as you're going down. You might want to say that I'll sort of backtrack, but in a priority-driven way. That I mean, if I had a partition, right? See, the problem is that when I have this partition, when I'm doing the partition, if the query lies here, right? Then, I mean, if I'm doing defeatist, then I'm only going to the left, but the nearest neighbor could be on the right. That is basically the problem, right? So therefore, I kind of have to do some kind of backtracking. How you do the backtracking? There are different variations, right? I mean, without going to the variations, the point is that this can potentially take O of n. It works fine in practice for certain kinds of partitioning, but all theory bounds that I know of is the worst case is O of n, right? Under certain assumptions on the data set, if the data set is nicely low dimension and all, you sort of do better, right? So again, it's sort of, this is a huge area of research, right? There are several variations of space partitioning trees possible. One of the very common ones that you find everywhere is KD trees, right? In which case the partitioning is basically axis aligned. Right? That is, you always partition parallel to the x-axis or y-axis or z-axis, I mean, according to that. There's something called a random projection tree, in which you basically choose the partitioning space, I mean, to be a random hyperplane, right? Yeah, you could use something called a principal direction tree. right, which says that, okay, look at the covariance matrix, try to partition it according to the eigenvector of the covariance matrix. You look at the two-main tree, which says that, okay, at every point, try to cluster it into 2 points and then look at the hyperplane that's separating the 2 clusters, okay. So, I mean, again, it turns out, if you're interested in this, it turns out that some of these have better theoretical and practical properties than others. There's something called intrinsic dimension, and it adapts to that and so on and so forth. So typically, if you want sort of I mean, rule of thumb, using principal directions or two means is much better than using KD trees. And random projection is better than KD trees. Almost everything is better than KD trees, but KD trees is the most used. But okay, the other way, right? The other kind of data structure is what we have is a hash table, right? So what is a hash table? So hash table is very simple, right? All of you know what a hash table is, that I'll take the points, I'll have a hash table, I'll map the point to one of the buckets in the hash table. So what happens when a query point comes? Okay, when a query point comes, I'll again map it to one of the buckets, and then I'll again only look at the points that I've mapped into this bucket. I won't look at anybody else, right? For instance, if the query point comes, if the query point lies here and it's mapped to here, right? Then some of these points will be mapped to this bucket, and I'll only look at the elements that I've mapped into this bucket. No one else. Okay? Let's say that this is my algorithm. So what do you want? I mean, how should the hash table look like? What kind of property do you want of the hash table? See, our typical construction of a hash table is that it should spray the points uniformly among the hash buckets, right? Because we want the load to be sort of the maximum load to be close to the average, right? So what we typically want out of a hash function is that it should pick a bucket more or less uniformly at random. We don't want that here. Here we want something special out of the hash function. In fact, what we want is something that says that, I'm not showing it sort of mathematically. Here we want something that says that, okay, if 2 points are close enough, right, they have a good probability of mapping in the same hash bucket, following the same hash bucket. That's what we want out of my hash table here, or of my hash function rather, right? And if I have this guarantee, right, then if I map the query to one of the buckets and look at only that bucket, I have a good chance, right, of finding my near neighbor, or at least finding somebody that is close.
So,
yeah.
So do all the buckets have the same number of points? Or
no, they do not. It depends on the structure. So all the buckets do not necessarily have the same number. So first of all, this is a random function. But even in expectation, they might not have the same number of points. Anything else? Any other question? Sorry, maybe I'm rushing it through. So intuitively, what we really want is that if points are nearby, I want a high probability of collision, which is not the kind of hash functions we were dealing with before. This is called locality sensitive hashing. Okay, and this is pretty bad. Okay, so how will it work? Oh, maybe that's what happened. Maybe it sort of vanished. The picture was somewhere, but yeah. Okay, so how do we create this? Just in a 30-second slide. I mean, if you really get down to the basic of it, it's not very different from one of these tree constructions that we were doing, right? What we do is that we again create this random partitioning of space, use that to create use let's say the idea of the Voronoi, idea of the cell, right? Because this partitioning of space creates these cells, right? So basically use the idea of the cell as the index of the hash bucket, right? And then you have to repeat this process, because this gives you only a sort of probabilistic guarantee, right? So you have to repeat the process number of times, but still it turns out that even theoretically you can get an astonishing result. You can say that let's say in two, if you want a two approximate nearest neighbor, right? What does the two approximate nearest neighbor means? Means that if your nearest neighbor is at a distance r, I can guarantee you that I'll return you something which is distance no more than 2r. If you want a two approximate nearest neighbor, you can answer that in times square root n, right? Which is pretty interesting. And in fact, you can probably guess that this 2 is connected to the half that I've put out here. Okay. So anyway, so basically here is where we step from the theoretical side to the more practical side. Okay? So it turns out that what I'm talking about is very, very practical, right? If you talk to people in Spotify, which is why the city of Spotify developed this, if you talk to people in Flickr, in Google, Microsoft, these algorithms are used every day, every second, right? And so it's not enough to prove the kind of bounds that I showed out here. You have to make this work in practice very, very fast. right? So there is, I mean, if you look at the number of papers that have come in, I mean, even in fact, there's something missing out here. Okay. There's a huge number of papers that come out in this. And the question is that how do I know which one to pick as a practitioner? Because I don't want to read 10,000 papers. So it turns out that there are different ways of comparing, right? Because there are different parameters that we are juggling together, and it's not very easy to compare. So what are the parameters? Let us consider, right? So typically what you would see is that, so what is my primary interest? My primary interest was reducing the query time, right? But I'm also interested in the space of my data structure, because practically I don't want to keep a huge data structure, right? So there is the space of the data structure, there is the query time, right? Then there is also the question of accuracy, because if I don't return the exact nearest neighbor, how bad is my solution, right? So these three parameters you have to kind of juggle to find a sweet point. And you could juggle them different ways, and depending on the resources that you have, depending on the practical example that, I mean, depending on your particular example, you could, for instance, not worry about space. Say that, okay, I have a half terabyte memory machine, right? And then I only need to compare the query time speed, right, with the, while keeping the accuracy same. Then and this is how I compare the different algorithms. So given that all of them are returned, let's say, to approximate nearest neighbor, I compare how fast is it, right? I could compare the accuracy while keeping the space usage to be the same, right? I could give everybody a common space bound, right? Say that, okay, all of you have to work in 64 gigabytes, and then compare the query time versus accuracy, right? So here is one way of doing it, right? And this is the way that this particular Python package that I'll talk about in the next two slides does, which is to say that okay, I don't care about space. I'll compare this plot. I'll look at the one nearest neighbor accuracy, right? So the farther away in the x-axis you are, in this direction you are, the better you are, right? And this is the y-axis, number of queries per second, right? Basically the query time that I was talking about, right? So high up is you can handle more number of queries per second. Okay? So basically a curve out here, all right, which is further up and further right is better. So a point here is better than a point here. Okay? And so the problem that I was talking about is that this number is not visible here, but if you search today for approximate nearest neighbor, you get approximately 300,000 articles, right? 300,000 different algorithms, right? And they're all variants of, let's say, hundreds of algorithms. There's few parameters for each algorithm. There's hundreds of data sets, and there's lack of clarity of what to use, right? I talked about these two variants. There's also a set of graph-based hashing, and how to even compare, right? Even if you look at the set of papers that are coming out, let's say in KDD or WWW or something, and propose a new algorithm, how would you even know what to compare, right? And in here comes these three characters. So this is Erik Bernhardsson, who used to work in, who was the CTO of Spotify, and he used these two very nice tools, a combination of Python as well as Docker. So does anybody know what Docker is? Okay. So I'll give a very one line. I don't know myself a lot. So so think of it as an application level virtualization. Basically, what it says is that if you everybody knows what a virtual machine is, right? So virtual machine is essentially that you're running an entire copy, an entire instance of a guest operating system as well as its applications on a machine. A Dockerization says that the operating system kernel is the same, right? But beyond that, it's providing you a sort of containerized version of what you really need. So what does it mean? What it means is that if I Dockerize my sort of application, what it means is that I can just and I can put it on Docker Hub, which means that everything that I need, any libraries that I need, will be within that Docker. So all everybody needs to do is just attach to that Docker, right, that I have created, and then it will run on the system. Right? So this very nice, so this Erik created a very nice system called the ANN benchmarks, in which he has put a huge number of algorithms. Right? He's basically Dockerized all of it and put all of them up in this public domain, and along with a bunch of data sets. Right? So now all you need to do, if you have a new algorithm, right? So this is how to run it. It's like 3 lines. You install Docker, which is pretty simple, and then you clone this, you install this, and then you just run python.run.py. At which point it might sort of get stuck for a few weeks. It did get stuck for 2 days in my computer, and then I killed it. Because, it's a huge number of data sets. I didn't realize how many data sets it is. So including an algorithm is very simple now. right? You sort of you run a few scripts, Docker scripts, and then you can sort of add it to his sort of to his library, to whatever this Git thing that he has, right? And it immediately generates all these this plots about, I'm sorry, all of these are very bad, this thing. So this is the plot of the recall of the one nearest neighbor accuracy or recall versus the speed, right? And now this is comparing like 40 different algorithms out here. Well, not 40, like 10 different algorithms out here, which it would be very painful for you to compare if you are developing a new algorithm. In fact, the reason that he came about was that for a while he sat down, he claims that he sat down for like 2 weeks and he had the best performing algorithm. He's being a gracious person himself, he's also sort of updated it, think that the best performing algorithm is somebody else's. But all I'm getting to it is that this is really the right way of doing data science, right? That it's not enough to actually come up with an algorithm, you should also sort of develop this kind of tools to actually show that why it works and just, prove in sort of set in stone that it really works. Okay, so I won't sort of drag it on. Sorry, I have exceeded my time limit. But it is the summary that we handled this nearest neighbor question. This is one of the core techniques in data science, machine learning. Much research has been done, of course. There's a huge amount of things that much is unknown. We don't know how to do it in distributed settings, so on and so forth. For non-Euclidean metrics, it's very hard. I think this is one of the excellent examples of a smarter algorithm plays an immediate role in making techniques efficient, right? And this package that I showed, this is one of the very nice examples I see of the right way to do this empirical algorithmics, how to sort of actually implement things in practice. Okay, thank you. Any questions?